Uh, Sorry. Oh, all right. Um, okay. Hello, everyone. Welcome to my talk. Today, I'm going to talk about ZKVM design trade-offs and our ZKVM, which is called Valida, the design considerations and choices that we made. And this is a joint work of 8 of my incredible teammates. Yeah, and then let's start. So yesterday we released our alpha ZKVM and our C compiler toolchain. I just wanted to show some impressive benchmark. So on iterative Fibonacci, we have up to 260x performance improvement over alternative solutions. And on SHA-256, we have up to like 54 times faster in CPU wall clock time. And this is CPU efficiency. This is like thousands of X of efficiency improvements over other solutions. And this talk, I'm going to talk about first, why we adopted ZKVM instead of other solutions, for example, DSL, direct compilation. And then second of all, what were we thinking when we were designing Valida? So what are the criteria that we were looking at, and what are the problems that we were solving? And third is like, right, our design trade-offs. How are we making the trade-offs to achieve such performance? And fourth is like some of our design choices, and then I'm going to show the demo, and then talk about our future directions. So the first question, I'm just going to skip really quick because I have a lot of slides. So what's the motivation behind ZKVMs? How do you prove succinctly in zero knowledge that a certain program was executed on a certain input and it had a certain output? So this is the motivations behind we're building ZK, I guess, in general. And the problem with this is that right, the learning curve, the tooling is really steep. For example, Circom and a few other libraries are require developers to learn right, new languages, or they need to write handwrite circuits. It's pretty time-consuming and requires a certain level of expertise. And then second is the high time, space, and energy cost of generating proof. And we think that's right, the motivations of behind this project. There are a few like approaches. I listed 3 here. So people who tried DSL before, that includes like Cairo, RWorks, and Circom, and a few others. There are people who tried direct approach. Actually, Anoma has a project that's been working on this direct approach, which is like compiling to a functional language directly. And then there's this ISA VM approach, which is Valida, RISC-0, SP1, Polygon Maiden. And we think that the right, ISA VM approach is right, the future, will be the dominant way developers interact with zero knowledge, because it's more developer-friendly, productive, and it's much more secure. You don't have to audit all the circuits to make sure there's no bugs. We only need to like audit the VM, formally verify it, and so it reduces the space that bugs can happen. And here we listed some like limitations of existing ZKVMs. Just a few, like for example, right, Cairo required developers to work in a unfamiliar like language model, and second of all, like none of this other ZKVMs are fully open source. I think right now SP1 is open source, but most of our VMs are partially closed sourced. Therefore, you can't even like add sort of some like optimized circuits to their libraries and stuff. And third is there are a lot of inefficiencies in other ZKVMs designs. For example, memory models in some VMs, and most of VMs are targeting like RISC-V, which is instruction sets that's targeting at hardware settings and not in ZK settings. And then the fourth is very difficult to, it's not modular enough. It's very difficult to integrate advancements in ZK. So for example, right now we support small fields for a lot of other VMs, one or two. It's harder for them to adopt newer techniques in cryptography. Therefore, we need a VM that's more extensible, more performant, and more developer-friendly. And now I'm just, after talking about the existing problems, what are the main criteria for evaluating ZK VMs, right? So there's baseline, which is like, it needs to be correct, it needs to be secure, and to consider a ZK, right? To be considered a ZK VM. So it measures the reliabilities of a ZK VM. And then the second is performance. So baseline include like correctness, security, and trust assumptions. And performance measures the capabilities of a ZK VM. So how efficient, how energy efficient it is, how performant, speed is, like how fast it is, succinct. How succinct is the proof being generated and verified. And the third is developer productivity, like how easy to use the ZK VM is, which includes like compiler, toolchain support, whether it supports high-level languages, and how easy is it to write, what's the UX for using those libraries, and modularity, so like how easy it is for developers to add like a certain specialized circuits for some use cases that want to work on. So this is our three main criteria. So just briefly talk about like what does each mean, right? So what does correct means? It means that the VM must execute the computation as intended, right? Then the proving system must satisfy its claimed security properties. And I'm just gonna skip this. Security means like how the tolerances of the soundness, completeness, and the zero knowledge. And then trust assumptions. It means like the assumptions about the honesty of the prover and verifier to reach the conclusion that the ZK VM functions reliably. And then, for example, that our VM uses FRI PCS, which has no trust assumptions, but some other ZK VMs use like KCG, which has trust assumptions, and then you need to do setup, trusted setup, and this is what this means. And performance. So there is a trilemma of like performance is it's speed, succinct, efficiency. So for example, if you like are much more performant, and usually it generates like a larger proof. So I'm gonna talk more about it later. But briefly go through the concept. So speed, it means like how quickly the prover can generate proof, right? So we measure this on wall clock time, which is the time from the start to finish off the computation. And efficiency means the resources consumed by the prover, and it measures by like user time. So for example, right, if you have like multiple cores, and if you're using 5 cores, and it takes like 1 second, right? So like it's more, the single core user time here is like speed. How we measure speed is like single core CPU proof generation time, and then the efficiency is core time efficiency and space efficiency. I guess we defined this two efficiency here. Succinctness means the size of proof generated and the complexity of verifying the proof. And it often includes the proof size and the verification time and the verification space. So like, I guess in conclusion, there are like 6 criteria that we're mentioning here, which is correctness, security, trust assumptions, speed, efficiency, and succinctness. I also mentioned the easy to use perspective, but I'm not gonna talk about it here. Okay, so here, this is like sort of the process of how we built the VM from ground up, and this is like providing like a sort of process flow. So we sort of you have to select the base proving systems, and then develop a ZK VM. So second of all, we develop a ZK VM with our own like ZK-friendly ISA instruction sets. And then the instruction set is actually tailored for maximizing the efficiency of zero-knowledge proving. And then third is we have to create a compiler toolchain to support high-level languages. Therefore, we are writing this LLVM-IR to our ZK-VM's compiler backend. And now we support C, we're going to support Rust and C++ and Solidity and other languages that has a LLVM front end. And then four is, we're also working on a hardware-accelerated ZK-VM proving system. Five is like formification. So EF right now is like working on this, and we're going to like collaborate with a few other like formification companies to work on this as well. So what are the design choices we have to make when you are building a ZK-VM? First of all, what instruction set architecture are you going to use? Right, and then we designed our custom like ZK-friendly ISA, but most of other ZK VMs chose RISC-V, some chose MIPS, I remember. And second of all, what languages support? Oh, well, this is more the compiler toolchain problem, and then third, should it be modular or should it be more monolithic? Fourth is what kind of arithmetization strategy should we use? Fifth is what field should the ZK-VM use for the arithmetization? And then what PCS should we use? And then what recursive proving should be supported? If it's supported, what approach are we taking, etc. So providing some guidelines. This is a general flow for how ZK-VM works. I'm not going to talk about it, but yeah. Okay, so in the second half of the talk, I'm going to talk about how we sort of build this VM, and then what are sort of why are we thinking about like sort of designing our own ISA. And so this is just a interesting like notes that we're just thinking yesterday actually. So we were like discussing like with my teammates that like what are sort of the key paradigm shifts in like instruction sets design and adoption. And we observed that from like 1960s to like 2000, there is like a general shift, right? So like we used to use like complex instruction sets, and then we're gradually moving to like RISC, like reduced instruction sets. And then we moved from like vector processing to like more scalar processing architecture. We moved from single core to like multi-core. We moved from fixed instruction sets to more extensible and modular instruction sets. And then we moved from general purpose to like more domain-specific architecture, such as like TPU, GPU, AI-related like chips as well. And then we also moved from like power agnostic design, like we used to not care about like efficiency, right? Now we care a lot about how energy efficient the chip is, and a few other observations. And then this is actually one of the reasons why we sort of designed our own instruction sets is because we think that under the paradigm shift of cryptography, of trustless systems coming, we think that there needs to be a new instruction set that's fit for this specific application. And that's why we sort of designed our own instruction sets. And like a few sort of basic question we were thinking every day is like, what instruction sets are more efficient to include in the ISA and to check in the star constraint system, and what are more efficient to just exclude from the ISA and eliminate from the compiler output by reducing them with the sequence of instructions, right? I guess the general thinking is that the differences between the ZK-VM computing environment and the hardware environments are very different, and that sort of drives our sort of different ISA design decisions. So our Valida ISA is a ultra, we call this ultra RISC, means like ultra reduced instruction sets. We only have about like 20, I think, instructions. And it's very modular, it's very secure-friendly, and includes the following modules. It has a 32-bit LU chips, and a CPU chip, a memory chip, a program chip, and an 8-bit RAM checker chip. This is a diagram of a basic Valida VM, what it looks like. And a few interesting points. So for example, we have two special purpose registers. We have no general purpose registers. And that's because it sort of simplifies the code generation by eliminating the need for the register to be saved and restored in the calling convention. And therefore eliminating the need for a register spilling the code to be emitted. Another point is we only have 2 RAM addressing modes, and the program ROM can't be addressed. And there is no dedicated SP register. The calling convention uses constant size stack frames. Right, so this is the overview of what the VM is composed of. First of all, it has an execution engine, and it runs the Valida program and generates the execution traces. And then the prover proves the result of executing a program by proving this valid execution traces exist. And then the last step is verifier. It verifies that the results of executing a program and giving a proof of that verification. These are some parameters that we're using. I don't want to go too deep into it, but we're using this baby bear field. We're going to support Merson field 31 field as soon as well. And the current PCS we're using is Fry. We are integrating with Basefold, which is authored by one of our teammates, Haras. I'm just gonna skip this. This is sort of how the prover works. Some techniques of optimizing the prover. So the Stark we're using is very efficient, and the only expensive operations it uses is a hash function. So we use gates with degree at most 3 and keeping the FFT and hashing costs as low as possible. So that's one of the techniques. This is just giving a few examples. And the second trick is that we use a finite field that's extremely efficient. Right now we use, as I mentioned, Baby Bear. We're going to support Merson field. And this is the compiler backend. So we are writing this LLVM IR to RVM compiler, and this is sort of how the LLVM toolchain work. So we're writing the LLVM Valida backend, right? And these are all existing toolchains, right? So LLVM already support C, C++, Rust, and all we're doing is to write the LLVM Valida backend, and once that's done, it's function complete right now. But the point is the unlock is that we can support C, C++, Rust, and all the other languages that are supported by LLVM. And the implementation is fully open source. You guys can check it out at Valida XYZ, Valida. We also, the LLVM repo is under Lita. Yeah, so it's highly customizable. I want to emphasize developers can just use the included compile time macros to generate with a little coding, and then you can just add the chips that you want it for your own use case, and it's highly customizable. The demo, want to show this. And another, okay. So 2 minutes really quick. I'll skip most of part 2.
Hi, I'm Morgan.
Oh, sorry, the audio doesn't work. Yeah, it's all right. I'll just send you guys the link. You can check it out later. Okay. Ongoing work. This is more in the proving system side, but we are thinking about, well, we are working on multivariate prover snarks, and we're integrating with Basefield, and we are doing some optimizations on the Fry prover. We're thinking about using circle snarks, we're adding EVM verifier. We're working with a few companies on hardware acceleration. So this is what we're working on right now to further optimize the proving system side. And we're also building this on developer interface to help developers to even more easily work with our ZKVM. So this would be like a platform where you can build templates, and people can use other people's templates to build their projects. And so basically you can just pick whatever language that we support, and then use somebody else or some app level templates, and then we also have like an online IDE. You'll be able to build your projects here, compile, see locally the proving costs, whatever, if that's helpful, and then deploy on a platform, right? So on the platform, you can choose sort of the different hardware configs you want to use, the proof aggregation layer you want to use, and the network you want to deploy. So we want to support as many networks as possible. So that's pretty much it. Just emphasize that Valida is a extensible, performant, and developer-friendly ZKVM. We just launched our alpha, so welcome everyone to try it out and give us feedback. And we're hiring. So we're hiring a cryptography engineer, compiler engineer, and we're hiring for this innovation team, which is we wanted to do experiment on the VM and build interesting products. So if you're interested in any of these roles, let me know. And here's our contact. Thank you.
All right, that's a very wonderful talk by Ventali. I don't know if you have any question, you can raise up your hand. Okay.
Hi, thank you. I'm curious about, I saw the benchmarks were really good on the proving side compared to Jolt and SP1. I'm wondering, especially you talked about the trilemma. What were some of the trade-offs? For example, I know SP1 also uses Plonky3 stuff. So what kind of trade-offs were made, to improve the proving speed and
yeah. I think the main difference between us and SP1 is they're still using RISC-V, RISC-V instruction sets, and we are using our own sort of designed, custom instruction sets. I think that's a main differentiation. There are a lot of, the member arguments and a couple of other things are different too. But I think in the proving system side, eventually, everyone is going to, it will become a commodity, and everyone is going to use the most performant and advanced libraries. We are contributing to Plonky3, and we're working on a more optimized version of Plonky3. I'm not sure if, maybe it's called Plonky 3.5, but we're working on that as well. So we're going to integrate with a more efficient PCS called Basefold. So we're doing a lot of work on the proving system as well, but I personally think that a proving system wouldn't be a differentiator for any ZKVM. And every proving system is open source anyways. So I think the main optimization would be, for at least for us, would be from the instruction sets, and the compiler. We have to keep optimizing the compiler as well. Does that answer your question?
Yeah. So on the RISC-V, so you're saying succinct or SP1 is a RISC-V VM, and then that compiles to LLVM, whereas you guys wrote. I guess I don't quite understand what the RISC-V thing was, but
I'm not sure if they are compiled to LLVM, but I know they're using this either RISC-V or reduced RISC-V instruction sets. Yeah, but I'm not sure about the LLVM side.
Cool. Thanks.
Right. Any other question?
You said right now you support C,
Yeah, right now I support C.
but on one of the charts it showed that in any case, you go from whether C or Rust, you end up with LLVM code, right? So what needs to be done still to support Rust, for example?
What? Sorry, what's it?
Because from Rust you can already get this.
I guess we have to different languages have different runtime, and there's some work to do there as well, and we have to support some, because our Valida design is different from other VMs, so we have to. So for example, Rust standard library, we have to sort of fix some edge cases there as well. I think that's I don't work on the compiler side, but I think that's runtime, and then we have to support library functions on top of it. So we're working on sort of, for example, Rust standard library support and a few other support. Yeah.
Thanks.
All right, any other question? Okay, that comes to the end of the talk for today. Please, can we give Ventali an applause, please? All right, that's the final talk for the flower stage. So by 5 o'clock, we'll be having our closing ceremony in the root stage. So thank you everyone for coming to the talk, and I so much appreciate your presence. Have a good day.